Hi, my name is Nicholas Wiley, and this is Material and Energy Balance, Homework 4, Part 1. What we're going to be discussing today is a continuously stirred tank reactor. Now, what we're going to be doing for Part 1 is deriving the time-dependent material and energy balance equations of the system described. Now, what we have here is a bunch of information, a bunch of constants. Now, what I've done is I've put the constants here and summarized the information that we know. So, let's just get right into this. Let's first start by explaining the tank. So what we have is we have this system. There's a certain amount of material being put into it, and we also have this continuously stirring rod. So what this is going to ensure, which is going to be very helpful for our calculations, is that the temperature and the concentration inside of this is going to be the same throughout, which is going to translate into what is being pushed out of the system. Now, let's just get right into it. Let's start with our first thing that we want, which I've already crossed out. This is the second take. We have the rate of change of the concentration of A over time. So this is what we want. So let's just get this up here. This is what we want. Now, how are we going to get there? Let's start with something that we know. We know that I'm bad at pronouncing it, the Arrhenius equation is going to be very useful for this because we're going to need what it provides to figure out the rate of reaction and therefore what is the balance inside of our system. So let's just get right into it. So what we know is that the Arrhenius equation tells us this K value, this reaction constant. Now, what does this tell us? What is the equation? How is it written? So usually we'd have an A here, which is the Arrhenius number. Rather, what we have instead is a K naught value, which is a constant, which is very helpful for us. So this would typically be an A, but now we have a K naught. And we're going to multiply this by E raised to the negative, let's write it as it's supposed to be, activation energy over RT. Now, thankfully for us, we have another shortcut. On our constants, our constant conditions, what we know is that EA over R is equal to 8750. So we have negative 8750 over T. But you look at that, we're already making progress. So this is going to determine our rate constant for us. Now, what is also important about what we read in this brief description of what this problem is about is that this is a first order reaction, meaning that it takes 1 mole of A to go to 1 mole of B. Now, this is perfect because in general chemistry and chemistry I've taken in the past, I know this. So our rate is going to be equal to our constant times our concentration of A, which is very nice. Now, with these two things alone, I believe what we can do is we can figure out the material balance. Now, let's just start by talking about what this means. It means the rate of change of the concentration of A over time. So what this actually means, let's get some units out here, is we have moles per liter times 1 over minutes. Divide by minutes. Now, as this is a material balance class, what we would much rather prefer to do is we would rather balance moles than concentration. So it's the name of the class. So what we're going to do actually is to get it to be moles per minute, we need to multiply by liters or the given volume that we have, which is 1,000 liters, which I will not, 100 liters? 100 liters, not 1,000. Which isn't important for now. We're just going to call that V. Now, this is very beneficial because now we can go from concentration per time. If we multiply that by V, now we have a change in moles rather than a change in concentration. Now, something else we need to explain, I'm going to write this at the top of the board actually, is one of the biggest things about material and energy balance is that, it was taught on the first day, is that our accumulation is equal to in minus out. What's pumped in versus what's pumped out. But in this case, we're talking about concentration. There's also something else happening. What is going to change that concentration? Well, again, we have that reaction occurring. So therefore, we are going to have some loss due to reaction. So we're just going to add other out In this case, our other is the amount of concentration being lost during reaction. So, okay, let's move on with this. So now we have our moles per minute. And what we want to do is we want to balance this. So starting off, we need the in minus out. How are we going to do that? First up, what we're going to do is we're going to need Q. We're going to need our flow. So what this means is we're going to go for the in minus out. We already have the flow. Now we need to know what's being changed. And of course we know it's the concentration of A. So we have the concentration of A being pumped in minus the concentration of A being pumped out. Now there's no bracket, there's no close to that because we need to make a quick change, a quick assumption, a quick observation. Because we have a continuously stirred system on our hands, that means that the concentration of A being pumped out is the exact same as what's in here. So the internal concentration is the same as what's being pumped out. So we can just get rid of that out and call it the concentration of A. That's nice for us. Now, how else can we progress through this? So we had our in minus out. What's left? We need that other, which is that what is being reacted. So again, what we need is we are going to need our reaction rate. So we have K times Ca. Now, what are these units right here? What are these units? Now, K is, what is K? It's just 1 over minute. That's what that means. Because when you look at this, the rate is equal to the concentration per minute. So K is 1 over minutes, and if we do that, we're left at the same thing. 1 over minutes times moles over liters. So what we need to do again is account for that. Multiply by V. And now all of our units are the same. 1 over minute. Q is equal to liters per minute. Multiply that by the concentration, moles per liter. Oh, what did I say? I meant moles per minute over there. But again, over here, we're left with moles per minute, the way we've done this, which is perfect for us. Now we have our first equation. So what I'm going to do for simplicity's sake is I'm going to move this up here. I'm going to write it in red so I know not to touch it. We're going to multiply by V, so we get Q over V. Concentration of A minus the concentration of A in minus the concentration of A, which is the same as going out. And we are going to subtract K concentration of A, divide the last V. So now, properly cross it out now, we have our first equation, our first differential equation. I erase some of it. All right, so now that we have that done, the next thing we want to determine is let's write down here, what is our rate of change in our temperature inside of the reactor over time. Now, how are we going to do this? We need some more relationships that can build us to that relationship that we need. So from general chemistry, just chemistry I've taken in the past, a big thing that I've learned about is delta H. The name of the class is energy balance. So this is internal energy. This is exactly the direction we want to go in. And that is equal to mc delta T. So that's nice. What that's going to provide for us is going to provide another relationship for us, just like we turned the concentration over time into moles over time. With this is we're going to turn temperature over time into energy over time, joules over minutes. So what we can do is we can determine our left side with this, because we pretty much want delta H to equal delta H at the end of the day. So now that we have our temperatures per minute, what we can do is we can multiply it by the rest of this. All we need is that M and that C. But how are we going to get mass? We weren't given anything to help us determine. Or were we? Another relationship we've learned in the past is that density, rho, is equal to mass over volume. So that's perfect for us, because all we have to do is density times volume and we get mass. So that's another rearrangement we can make, because those were given to us, the density and the volume. So then we can multiply this, density times volume. So now we've accounted for the M as well, and the C we just put in there. So now we've effectively turned temperature over time into energy over time. And this is going to give us joules per minute. That is going to be the units we're going to be trying to achieve the whole time. So let's do this. Now, another thing we need to look at is what exactly is going to be balanced here. We have our accumulation is equal to in minus out. The in minus out isn't an issue. We just use the temperature in minus the temperature out. But what are those others that we're going to be looking for? Well, another key thing to this whole shebang is that we have a negative delta HR value. Okay, so that's our heat of reaction in a way. So what we also need to subtract is we're going to need, let's add a little air down here. So for this equation, our others are going to be 1 heat lost via reaction. Another point I don't know if I've made clear yet is that we have this blue liquid here cooling the system. We have coolant being applied. So there's also going to be some heat transfer, some energy transfer between some heat lost via coolant, or to coolant. So now we know our other two factors. Before we only had one other factor besides in and out. Now we have two other factors that we need to account for. Now the heat lost via reaction is not very difficult to figure out because we have this delta H. And again, we just have to transfer that into our joules per minute units. Now, how are we going to figure out the heat loss to coolant? Thankfully, we have a relationship that we know. So we'll call the heat loss, we'll call that big Q. Now, what the heat loss is going to be equal to is going to be equal to some proportional constant, right? Between the temperature of the reactor minus the temperature of the coolant. So now we have figured out the heat loss to coolant, the heat loss to reaction, and the in minus out. So now we just got to put it into numbers, into terms that we can understand and use in the future. So what I'm going to do is leave it all up here. So now we're at joules per minute. I'm going to make that a big deal because units are key in this. We need to make sure all units are the exact same. Now, what we're going to need is we're going to need that Q value again, which is liters per minute. I'm going to keep making this a big deal. And what we're going to be multiplying this by is the temperature that is being, the temperature of the material that's being pumped in minus the temperature of the material that's being pumped out. However, I've made it a big deal to this point that the temperature of this internal system is the same as what's being pumped out. So again, we can say the temperature of the reactor internal, say int. Okay. So now what's this going to give us? Q. Q is going to give us liters per minute. And now we're going to be multiplying by Kelvin. Now, how are we going to account for the rest of this? How are we going to account for this? So we have kelvins. Now we're at liters Kelvin per minute. That's a strange place to be at. Now the number one thing that we can use right here, very helpful, is the C value, which is going to be joules over grams per Kelvin. Right. So let's add that C there. Now if we do a little bit of crossing, we got the K's canceled out, but we're still left with liters on top and grams on the bottom. What does that open us up for? That opens us up for density. Grams per liter. Cancel, 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 cancel. Now we're left with joules per minute. We're happy. We got our units. So let's add a little row. Okay. Gonna erase that because we figured it out. Now rather than move to the right, I'm gonna move down here. So just add that little note. Now that we've accounted for the in minus out, we need to account for the heat lost via reaction. Now, what we need to do for that is, rather than subtract the heat lost, what we're going to do is we are going to add that number. Now, why are we going to do that? It's because it's a negative number already, so there's no point in changing it. So when we use this, we're at joules per mole. Now, how we again need to arrange this so that we can get this into our joules per minute. So luckily we have moles. So how are we going to do that? Well, we're definitely going to need a C value. Definitely going to need that C value. So we're at joules per mole times grams per, is it mole Kelvin? Joules per grams Kelvin. Okay. Now moving on, what else are we going to need? Is that correct? Joules per mole. Well, let's push that to the side. What is that going to be dependent upon? This is going to be dependent upon the concentration of A. How much is reacting, giving us that energy gain, energy loss, that exothermic energy being lost. So of course we're going to need the concentration of A, which is going to help us a lot because we have moles per liter. Now, if we want to get this to, we're going to need to, so we have the concentration of A, and we're at, the moles are canceled out, we're at joules per liter. Now, what is the best way for us to get rid of that? I believe that the best way for us to get rid of that is for us to, multiply by Q, of course. Not multiply by Q because that's our flow. Again, that's our rate. We need that rate in there, which is liters over minute. Oh, wait, would you look at that? Oh no, don't look at that yet. Our liters have canceled out. Oh wait, no, that is, yeah, do look at that, actually. Now we have figured out what we need to multiply the enthalpy by. Now I know that was a lengthy explanation, but again, even if you don't know 100% what you're doing, what you do is check those units. It's so important for you to do that. So now we're there, we've figured out that. I'm going to rearrange QCA. So now we know that value, and again, what we need to do is we need to figure out what is lost to the coolant, which, again, we have right here. So we are going to have the minus UE TR minus TC. Now, again, what we need to do is we need to figure out those units. So what are our units for, is it UA? It is UA. Oh, that's a terrible mistake. So UA is equal to joules per minute K. And what we're going to be multiplying that is K. So would you look at that? Cancel out the K's and we're back to joules per minute. Now we have everything lined up. And this is going to be our second equation. Now what I could do is I could go through and divide, but this video's gone long enough, you'll understand what I'm going to do. I'm going to isolate the rate of change of the temperature of the reactor over time. And so I'm going to divide by rho V and C. And then we're going to be isolated with that, and we're going to be left with our first equation and our second equation. Thank you for watching.